It depends on what's on the screen. Okay, so today we're going to continue talking about sort of offline analysis of music audio. Last week we spoke about rhythm tracking, which was, the sort of fairly simple piece of information we're trying to get out of the audio, which is where the beat events occur. That was sort of historically one of the first things that really got going because it's relatively low computational intensity. But of course, the things that we're sort of more interested in, and probably the stuff that's people started looking at earlier, is looking at the notes. But it turns out notes are pretty hard, but maybe we don't need the individual notes. Maybe we can look at the combinations of notes, which have this big, important contribution to musical flavor, and we can describe that as trying to track the chords, trying to, the harmonic function of the notes. So I'll talk about the general problem of representing music audio, and then we'll talk about these chroma features, which are these really nice, really useful features for recognizing chord-type things, and then some chord recognition systems. So last week when we were looking at beat tracking, it was very much, looking at individual tracks, and then maybe you could imagine some kind of application where you're trying to synchronize beats or find pairs of tracks that had the same tempo so you could match them up. But a lot of the application of music audio analysis is thinking about very, very large music databases, and then the information retrieval problem in music. How can we take this collection of 1,000 or 10,000 or 1 million tracks and give someone a way to navigate and find items usefully? It's very easy to come up. It's, the best music expert can maybe, think about 10,000 tracks. That would be hard, but they might be able to come up with suggestions from that kind of scale. But the actual available music database is 1,000 times larger than that. So there's no way that any human can keep track of all that data. The only hope we've got to be able to find things arbitrarily within a data set of that size is some kind of computer-managed access. So there is this kind of general idea underlying all this work that is, well, we're going to take our individual piece of music, we're going to calculate some features for it, but it's going to be a fixed number of features, and it's going to be a relatively small number of features compared to, the actual description of the audio, which is millions of frames or something. If we can just bring this down to dozens of dimensions, then we can imagine arranging the music in some kind of Euclidean space where each of these dimensions is now a separate dimension, and then trying to structure it such that the different regions of this space correspond to different kinds of music, different similar pieces of music. And this is, this is the whole statistical pattern recognition paradigm where you try and have this feature space that is relevant to your task. And if you could do that, then you could do things like saying, oh, well, if you're interested in this kind of music, if you like this track, then maybe you like these tracks around here, or if you're trying to make a playlist based on this track, then we can take the near neighbors should be relevant and good choices. So if you want to do this, then we have to figure out what the dimensions are going to be. And depending on what we decide, then we're going to get different kinds of spaces in which different kinds of things end up nearby or distant. And so we could say, well, we're interested in the general sound of the piece, which, the musical term for that is timbre, which means the kinds of instruments that we're using and the way they've been recorded and produced. And if we're interested in that, then we can start looking at these Mel frequency Kepstrel coefficients, which are derived from speech recognition, but in speech recognition, they're a very efficient feature for capturing the rough overall character of the sound, the things that distinguish different phonemes from each other. Maybe we're not so much interested in the instrumentation, but we're more interested in the notes, the melody and the chords. And if so, then we have this different feature called the chroma feature, which is only one of, so it's a particular choice, but as we'll see, its goal is to try and separate out the the information about the pitches from the information about the instruments and what's carrying the pitches. And then, maybe we're interested in rhythm as well, and we could think of a bunch of dimensions to do with the rhythmic character. I mean, last week we had like BPM. It's kind of one dimension, but if you wanted to get some kind of different feel, you could imagine taking a normalized chunk of, say, the autocorrelation, time normalized, and then using like a few low-order Fourier components, something like that, to describe, where the energy is within a single bar or something like that. So these are all choices, and we can end up with these pictures, but just the pictures are going to be different every time. And of course, this picture was generated by this software called Gobi, which is just this way of visualizing. You load in the high-dimensional set of features, and then you can select which ones to project onto your two-dimensional plane, and it gives you this very nice kind of simulated 3D visualization. But at the end of the day, you can visualize it, but if it's 100 dimensions, it's very difficult to find anything terribly meaningful in that. So MFCCs, I mentioned, are the features that we can use for getting the overall sound. And by that, I mean the smooth spectrum, the broad structure in the spectrum. And of course, the broad structure in the spectrum is the thing that we use to distinguish speech sounds. It's the resonances in the vocal tract, which we learned about, give rise to these sort of broad peaks in the spectrum of speech. And so our ears are sensitive to that in order to distinguish different speech sounds. And then in speech recognition, the problem is, well, how do we capture that in a way that is sensitive to those changes, the ways that people pronounce different words, but not too sensitive to the different ways that people pronounce the different characteristics of voice, because we want the speech recognizer to know that we want to have speaker-independent speech recognizers so that it recognizes the word even if it's being pronounced in different ways or by different people. And it turns out the basic answer to that is just don't keep too much detail in the spectrum. Smooth it out. Just keep the broad spectrum, and then that basically does what you want. And so the way that we do that, we take the FFT to get the regular sort of high-resolution spectrum, typically on like a 25 millisecond window. Then we do this Mel scale frequency warping, which is just a warping that reduces the amount of the spectrum which is used for the high frequencies. So in a regular FFT, if I take it on a signal that's sampled at 16 kilohertz, then my Nyquist rate is going to be at 8 kilohertz, and my spectrogram is going to have the bottom half be 0 to 4 kilohertz, the top half be 4 to 8 kilohertz. It turns out that from a listener's point of view, the difference between speech which is at 8 kilohertz bandwidth and speech which is at 4 kilohertz bandwidth, the 8 kilohertz bandwidth sounds nicer, it sounds a little clearer, but the 4 kilohertz bandwidth is fully intelligible, still sounds like basically all the speech. Maybe a naive listener would have difficulty telling you what the difference was between those two. And so rather than being 4 to 8 kilohertz, rather than being half the information, it's like 10% of the information. Difficult to measure that, not sure what I mean, but it's clearly not half the information. And so the Mel scale just re-warps that, so you have a lot of bins in sort of under 1 kilohertz, but then above 1 kilohertz they become progressively broader, so you have less information allocated to these less perceptually important high-frequency bins. So this is the picture over here. This is the time waveform. This is the FFT, and looking at the blue, here's the FFT, and you can see because this is like a vowel that's periodic. The FFT has a bunch of the DFT. The Fourier transform has a bunch of peaks, equally spaced, which are the harmonics of this thing. And here's the Mel warped spectrum, where you can see now these ones are kind of further apart, and then they get closer together because now we've got less sampling for the high frequency, and this part's been stretched out to occupy more of the spectral axis. So this is still magnitude, it's the magnitude of the complex Fourier transform values. So then we take the log magnitude here, which is, these are the same peaks, but now because of the log sort of condenses these parts and stretches out these parts. So we see them sort of looking slightly different and more detail down here, and then these wide variations in the peak height are more condensed. Of course, with the log axis, there's no zero reference point. It's whatever scale you want to show. But the point about the log is that these parts up here, which have almost no weight compared to something down here. Now they're lower down, but they're still deep notches, and so you can still pay attention to them, and that's perceptually important as well, that our sensitivity to energy is more logarithmic than linear. So this is a nice spectrum. It's the kind of spectrum we would typically plot, a log spectrum. But then what MFCCs do is they basically take a Fourier transform of this blue line, which is, again, you just describe this spectrum with a set of sinusoidal bases or cosinusoidal bases. In general, this thing, it's going to have negative frequency components because it's a real signal. They'll be mirror image. Their magnitudes will be mirror image. So taking the Fourier transform of this is actually the same as taking the cosine transform because only the cosine terms are going to be non-zero. Or you can think about it as taking the inverse Fourier transform because, of course, Fourier transform and the inverse Fourier transform are both just expanding a signal on sinusoidal bases. The interesting thing about thinking of it as the inverse Fourier transform is that now you realize that this axis is back to being some kind of time-related axis. It's not time because it's the Fourier transform of a Mel scale, not a Hertz scale. So it's something weird, but it sort of has a time structure. And so here, you see there's this kind of pulse out here, which is not strictly related, but maybe somewhat related to the periodicity in here. So it's a bit like an autocorrelation. If we took the FFT, took the magnitude, then took the inverse FFT, we get the autocorrelation out. But here we're taking the FFT, doing a frequency warping, taking the log, then taking the inverse FFT, so it's something else. But it's something like that. The value of this is that these low terms are the typical low-order Fourier terms. So the 0th term is just the average level. Then the first term is like, this cosine basis, the slowest cosine basis you can have, and then the second term is like the second cosine basis, something like this. And so they're just if the point here is we can truncate this representation at some order, and what we'll get is like a Fourier series approximation to the blue signal. And so that's typically what we do, that in general, if you have 40 or whatever this is, I don't know what this is. It looks like it's more than 5 values here. So if we have 100 samples on our Mel spectrum, then when we take the inverse FFT, we're going to get 100 points. But if we just keep the first 12 of those, then we have a low-dimensional representation, and what it's captured is kind of like the broad structure. So that's what the red line here is doing. It's taking, I think, the first 12 coefficients and then reconstructing, going through every step. So now when we have this 12th order Fourier basis approximation, we get this thing which looks kind of like, you can sort of see the individual sinusoids in here. So it's unable to capture this rapid fluctuation from the harmonics. It just captures the sort of the general shape. There's some peaks down here and a peak up here, and it sort of goes down. And then if we undo the Mel warping, if we undo the log, it looks like this. If we undo the Mel warping, it looks like this. We can actually find a time signal that has this spectrum, right, by trying to find like a minimum phase fit to that. And that's what the red signal here is. That's not particularly interesting. But this is kind of the point, that what we've done is we've gotten an approximation to the spectrum, but in this case it hasn't preserved the pitch pulses, which is why we use it in speech recognition, because now we have a representation of spectrum that is independent of pitch or has removed a lot of the pitch correlates, as well as any kind of fine structure in the spectrum that's specific to a particular speaker. Now, all that to say, well, that's great for speech, but why would we want to do that in music? And it turns out that there's not a good argument why you'd want to do that in music. But people tried it because they had the speech recognition tools laying around. In particular, Beth Logan, back in 2000, had this very important early paper on just trying out the speech tools on music. And it worked. And it worked in the sense that if you take a task like trying to distinguish pop music from classical music, then using the speech recognition approach, which is you convert it into MFCCs, then you sort of look at the distribution of those MFCCs, that works pretty well. And now we've had a chance to think about that. And the reason is, as far as I understand, that if you've got a particular instrument, then again, the sort of the overall shape of the spectrum of that instrument even if the instrument's playing different notes, the overall shape of the spectrum stays about the same. And so the MFCCs are good at capturing instrumentation. They can tell you, they don't worry too much about modeling individual notes, but if you have a bunch of different pieces played on the same instruments, the MFCC features are going to say, yes, they're all basically doing the same thing. And so if you can figure out what instruments are being played, then you are 90% of the way to just saying what the genre of a piece of music is. And so that stuff works pretty well. So here's an example of it's a nice way to illustrate what the MFCCs are capturing. So here's an original piece of music. It's the opening, 8 bars of Let It Be by the Beatles. And here are the MFCCs, and so this is just, this is a log scale spectrogram. So basically, we're just taking the Fourier base, the DCT expansion of each of these columns, and so here's the offset, the DC component, here's the first component and the second, etc., up to, I guess, the 12th component. And then I can take each of these and I can undo them, reconstruct the spectrum like I did in that previous slide. And then I can use that, and this is like for each individual time slice, so this is like for 10 millisecond slices or something. I can then take white noise and modify its spectrum to match what comes out of this MSCC, and I can generate a new time domain, a new actual audio signal, whose spectrum matches these MSCCs, but nothing more, right? The finer detail is all just noise. And then if you listen to that, you sort of hear what's been captured by the MFCCs and what's been lost. So this is the original. Which I assume is familiar. We're going to wait till a voice comes in.
When I find myself in times of trouble, Mother Mary comes to me, speaking words of wisdom, let it be.
So it's quite nice. That's a relatively simple piece of music, right? Just piano and voice. So the piano is playing chords. And here we can see these individual harmonics. On the log scale, we can sort of see the low ones quite clearly, but there's plenty there. And so it's not, if all you had was a printout of this, and you were asked what was being played, you could start looking at those harmonics, and you might actually be able to figure out they were C major chords. And then in here, this is where the voice comes in. There's some more stuff going on up here. And if you actually know what the voice notes are, you can sort of see the harmonics there, because the piano, of course, piano note, very rigid pitch, so these things are nice and flat. But once the voice comes in, you see these more fluctuating harmonics, because the voice will change its pitch dynamically. Okay, so that's what we start with. Do the MFCCs, reconstruct, and so then what we've got down here is following the time course of these signals, this sort of the short time energy quite accurately, because it's updating the amplitudes every 10 milliseconds. But it's got the spectrum is much less, as we can see, there are no harmonics visible here. It's got the general shape, but it's sort of washed out all the pitch structure. So that's the amazing thing, that you can still understand the lyrics, right? I mean, that's this is a highly biased experiment, because, of course, you're all remembering the previous version, which you're already familiar with when you're listening to this. But it is remarkable how this sort of justifies their use in speech recognition, that when you do this with speech, when you do this through synthesis, people have no trouble understanding it, because, in fact, yes, the MFCCs do capture all the information necessary to recognize the words being said. And even in this, where it's words mixed with piano and all the usual things that we'd expect that were important to help you separate out those two different sources, they've been highly corrupted. You can still understand the voice, and even though the piano just sounds like these weird kind of percussion things going on. But I just think it's really cute how you can still, under the right circumstances, you'd be able to recognize a piece of music even after it's had this done to it. But the argument here, the way that they're used is, well, more to the point, you could recognize the genre. I don't think you would. I don't think piano is the first thing that people would think of when they heard this intro. But it turns out that that's enough information for you to be able to distinguish a piano from, you know, guitars or something. So what are the things you can do with this? So there's been a lot of work done with this kind of representation and on these kinds of tasks. And so here's one example where we were trying to do artist classification, seeing if you can tell just from the audio, you can figure out which band it is or which singer it is. It suggests speaker recognition, right? It's the analogous problem in speech. Although I don't think we were trying to actually at one point we were trying to do, you know, figure out where the vocals are and just do straight up recognize the individual singer, but you get better results if you look at all the music and then also do instrumentation recognition. And so for this we had a database which was 20 different artists. We had 6 albums by each of these artists, so they were limited to artists for whom we had a lot of albums to hand. And so we had like 1,400 something tracks, I forget what it is exactly. And then for each track on the album, so the unit of classification is entire tracks. For each track, we calculate the MFCCs just like in the previous slide. And then for that, we just take that entire, you know, like if it was a 200-second track, it would be 20,000 individual 10-millisecond frames with a 12-dimensional, or 20, I think we use 20-dimensional MFCC feature vector for each frame. We take those 20,000 20-dimensional vectors, we just calculate their mean and their covariance, so 20 by 20 covariance matrix. So then we'd represent the entire track with like, you know, 60 parameters, half of which were redundant, right? No, sorry. 20 by 20 is 400, so it's like a 200 and something, 210 dimensions, 210 unique dimensions in the covariance matrix plus 20 mean, so 230 dimensions overall. But now we've got all our tracks as points in this 230 dimensional space. And then to 10 by 19, is that right? That's wrong, it's 10 by 21, right? Anyway, we would, to test this, you will have this kind of leave one out methodology. So you have a model of a particular artist which is trained on like 5 of the albums, then you take the 6th album, and you have models for all the other artists. You take each track off the 6th album, you see which distribution model fits it best, and then that's the label you assign to that track. And you rotate the albums, and you do it for all the tracks. And so for this particular experiment, we got 55% correct for artist classification, which is not, you know, dramatic. It's not like the 90% in the talk. But if you were just guessing at random, because this is a balanced data set, you'd only get 5%. So it's clearly much better than random. And here's the confusion matrix, which is, I mean, it's sort of been swallowed by the grayscale of the display. So there are some, it looks like there are some significant off-diagonal things here. But it's saying, you know, this doesn't look like guessing. It's definitely the majority of the mass here is in the leading diagonal where the actual label is the true label. But there are some artists where it does badly. So here we see for Led Zeppelin, for some reason, it's getting almost none of them right. Here it is getting, I think Led Zeppelin is still the most popular outcome for that data. But well, exactly. From the computers, like, yeah. So now we have the computer's opinion on what makes these artists unique or different. And so, yeah, it's a shame you can't see it. But so the popular confusions it's making are like, there's something wrong with this labeling. But, oh, wait, what? Green Day, Madonna. That's interesting. But there are, I think the labeling may be wrong, but like here it's confusing Madonna and Tori Amos. That's not bad, right? So it's the kind of thing you'd expect. Yeah, you can't see it, but there's like a spot out here, and so, you know, they're both female singers or whatever. And so some of these confusions make sense. And in general, it's not a ridiculous way to arrange the stuff. Yeah. Sorry?
What kind of parameters from the MXC analysis?
So the covariance matrix, right? This is what I'm... Okay, so how we did this is you have, so you're thinking about this cloud of feature vectors. Now it's a 230 dimensional, no, it's a 20 dimensional cloud. So we're taking 20 MFCC values for every frame. Then a single track is some large number of these things. Okay, so now I'm going to strip away the time, but now I've got several thousand points in this 20-dimensional space, and they're forming a kind of cloud. So now I'm going to say, well, I'm going to just model the distribution of that. So I'm going to fit a Gaussian to that. I'm going to find out where the mean of that cloud is, find out the covariance, and so now I've got this, high-dimensional but oriented Gaussian obloid thing. And so then I've got those for every artist. I've got these bunch of these little parametric distributions in my MFCC space. Now I have a new track coming along. It's got another cloud of points. And I'm going to see which of these models best fits my cloud of points, which you do by evaluating the likelihood of every single point and then multiplying all together. So you get the overall posterior likelihood of this set of observations given these models. And then you take the largest probability of that, right? And that's works okay.
Did you say 22 dimensions?
20 dimensions, yeah. So rather than taking just the first 12, which is what's typically used in speech, I used a few more. I used the first 20 dimensions, but it's like a 20-term Fourier approximation to the Mel spectrum.
So the dimension is different from the coefficients of...
No, that's normally, so they're normally called the Kepstrel coefficients, and you have, they're numbered from 0 to 19 or whatever. Yeah. So this works okay, but actually it's not. There are much better things now. This is a pretty simplistic piece of machine learning, because the idea that, well, there are these just clouds in space and that they're not, that I can model them with a single Gaussian rather than anything more complicated is not a terribly sophisticated approach. And so things can do better, but the idea is that maybe you can use Gaussian mixtures rather than single Gaussians, or what we actually do now is we support vector machines which are not trying to model distributions per se, but trying to find the boundaries between distributions, trying to figure out exactly where you have to pay attention. But it's still this geometric metaphor of how to deal with these sequences. Okay, so that's the general idea, and that, for artist classification, using MFCCs is really good, I think, because it gets the instrumentation. Although, if there's a lot of someone singing, it may also get at the character of their voice, or maybe there's a lot of discussion about the producer effect. It tells you about just how the guy in the recording studio liked his tracks to sound, kind of thing. But if you're interested in the notes, then we know that the notes are not there. We know from our resynthesis that the MFCCs has stripped out the notes, the individual pitches in the music. And so we shouldn't go looking for those. And basically, it's kind of interesting how this happened. There was this kind of existing practice. There were these tasks of genre classification and artist classification. And people were noticing that, there's no music in here. There's no melody. There's no tune in here. And so they started trying to come up with these tasks that would focus more on the musical content. And in fact, cover songs, which I'll talk about later, the idea of trying to find something which is the same tune but performed by different instruments was kind of a driving application here. But another thing you might want to do is just figure out the chord sequence. And that, we know that the chord sequence, the one thing you couldn't hear in Let It Be was the difference between the four chords in the sequence. They all sounded kind of the same. So if we wanted to get at that, we could just try and actually figure out what the notes were, right? So we could do something like maybe sinusoidal modeling. We could try and find the individual harmonics in the full mixture and then find sets of harmonics that were harmonically related and assume that there were notes present there. or there are other things we can do to try and do note transcription. But note transcription is really hard, and it's still definitely an open problem. Because you've got lots of notes in the same time and they're all overlapping. Often they share harmonics, so you can't even if you could pick out the harmonics, it's still kind of a tricky problem to figure out what notes are present from a list of harmonics. Here's just an example of a piano transcription system we made, and it's this is working pretty well, but it's still making these kind of unsubstantiated illusions because it turns out there's a note here, and so an octave above it has a high level of support because it's got all the harmonics present and stuff like that. So this gives a much too optimistic impression of what note transcription is like. But even under these nice conditions, we're making mistakes. So this leads us to chroma features, and the idea of chroma features is like, well, maybe we don't have to exactly find all the notes. Maybe there's something we can do which is a little less challenging, but that can still solve our problems of trying to find chords or trying to find cover versions of tracks. And so the idea of chroma features is, rather than having 100 or 88 semitones and trying to find the energy in each one of those, some of these semitones some of the notes on the piano are functionally kind of related. So in particular, if we have notes that are an octave apart, C3, C4, C5, they're all still Cs. And from a kind of musical role, in terms of like a chord progression, they are somewhat equivalent. That if you have a chord, you take out C4 and you put in C5, a lot of the character of the chord is changed. This was kind of, when I was coming at this a few years ago with kind of, I don't know what you would call it here, but like, middle school level music theory, I thought it's the same chord. And now, having worked with this, it's like, I guess there are important musical differences depending on which inversion you use. And so it's not the same chord, but in many cases it would carry the same label. At some level of transcription, it would carry the same label. So if we could just figure out what notes are present and not worry about what octave they're played, then we'd be a long way towards solving this problem. And so the idea of chroma is to do that. Represent what notes are present, but don't worry about what octave they are. And then in particular, those errors that we saw on the previous transcription slide where the note reported was an octave higher than the true note, that would no longer be an error because it would still be the same note. It would just be the octave that was wrong, but we're not reporting the octave, so we get it right. And so the idea here is that you have a set of semitone bins, and so under Western music structure we have the octave divided into 12 equal spaced bins, labeled A sharp, B, etc. And then we have a vector which says, well, for this note, it could either be an A at 110 hertz, or at 220 hertz, or at 440 hertz, or at 80 hertz, etc. We'll put them all in the same vector, and we'll say this is the vector of energy that represents A, and then we have different ones for each of the different notes. And if we have that's one way of thinking about it. The other way of thinking about it is for every frequency, the simpler way of thinking about it is for every frequency we give it some weight as to the amount of support it provides for each note. So and basically each frequency here we assume we can assign to one note. So if you heard a sine tone, what note would it be? And so here's my 110 hertz sine tone. It's like, oh, that's an A. And then here's my 220 hertz sine tone, oh, that's an A too. And my 440 hertz sine tone, that's an A. But my 460 hertz sine tone, oh, that's going to be a B. And so that's what this matrix is. So you take the spectrogram, you map it onto these 12 dimensions by having a NFFT by 12 matrix. And then you end up, for every column, for every spectrum, you've converted your 257 FFT bins down to these 12 chroma bins, which are showing you the amount of energy in each of the corresponding semitones. And so this sound example is like a piano chromatic scale. Over several octaves, well, over a couple of octaves. You know what a chromatic scale sounds like. And so here you can see the spectrum is getting higher as the fundamental gets higher all the way along. But here it's wrapping around, right? Because now there's no natural break here. This is a circular axis that the G sharp is adjacent to A. And so you see the energy here sort of forming this stripe, this helix on this circular scale. And all we're doing is just mapping each frequency to the nearest semitone, which is the it's this mapping. This is you can calculate it like this to get the integer bin that corresponds to it, and then sum them up over every bin in the spectrum. Oh yeah, So this is K is the FFT bins. There's some weighting here to sort of say that, well, very high frequencies don't have strong pitches. And then, it's B of this, which is like the bin. No, I don't know what that is. Yeah, here we go. B is the mod 12ness, and this is just converting it into an axis such that a semitone is one unit. So that's conceptually, I kind of spent a long time talking about that, but conceptually, I guess you get it, right? Which is just this mapping from a lot of frequencies to a few bins where there's a cyclic ambiguity from the octave. Now, it turns out that is easy to do, but if you just do it straight up like that as a nice matrix multiplier, so you just take the energy from the FFT and map it into the 12 bins, it doesn't work that well. You get, when you have, because the bins are log spaced, because the semitone bins are log spaced, right? The difference between two adjacent semitones is always 1.06, a factor of 1.06 in frequency. So, 110 hertz is an A, and then the A sharp of that is 116 hertz. But at, several octaves higher, 1,100 hertz is an A, but then the A sharp is 60 hertz higher, 1,160. Typically, but your FFT is giving you a fixed amount of resolution. It's going to be like one bin every 30 hertz or whatever. So at the high frequency, you've got plenty of resolution to be able to distinguish semitones. At low frequency, there's going to be some frequency you get to where suddenly the semitones become closer together than your FFT bins, and then you get this weird blurring, and if you're not careful, you can get bias to certain bins because they just happen to line up nicely with the FFT bins. And so there are a couple of things you can do. One of the things that I've had good success with is using instantaneous frequency. So rather than just saying, well, this is the 10th bin of the FFT, therefore its center frequency is 60 hertz or something, you actually look at the actual phase of successive values in that bin. You look at the phase derivative, which is the instantaneous frequency, and say, well, this is a 60 hertz bin, but actually the energy in it is advancing at like 70 hertz or 69 hertz or something. And so you can get below the intrinsic resolution of the FFT bins. And the other thing is that if you try and do that, you can say, well, I'm trying to look at the phase advance within these bins, but there's no real, it doesn't look like that these successive bins are related. And so you can filter out the non-tonal energy. It's a good way of deciding whether this energy should be included or not, or whether it's just like noise energy, which doesn't really have any pitch and so doesn't want to contribute to the chroma spectrum. So by doing that, we can end up, again, you can't see it so cleanly, but here, if you look on the previous slide, you could see this blurring to adjacent bins from these chroma values, but here the bins are much sharper, so it's just giving me a better, more discriminant spectrum here. Oh, the other thing that's important, of course, is that if you've got these chroma bins, which are saying, okay, if it's between 440 hertz plus or minus 12 hertz or something, then that's an A. Well, if it just turns out that the whole piece of music was played, tuned a little bit sharp, then you might suddenly start having a boundary between A and A sharp, which happens to sit very close to what you're estimating, and you get bins, you get values spilling out either way, and it turns out that's not that rare. So you need to have tuning that actually tries to figure out where the bin centers should be for the particular piece of music you're listening to, and making sure the quantization works for that. So we end up with this representation in terms of chroma, where we've got now, again, for every 10 milliseconds or something, you've got the individual feature vector, but now it's a 12-dimensional feature vector, saying the energy in C, C sharp, etc. And you can resynthesize that, do the same kind of trick we were doing before, just to see, well, what is the information that's captured. And the way you can resynthesize it is by saying, well, all I know is there's some energy that's meant to be at C. I don't know which octave it is. So I'll modulate it onto all the possible sinusoids that carry C. And so, this is not a C. This is whatever it is. Maybe it's a C. Yeah, like 520 hertz and 1,040 hertz and then 2080 hertz, something like that. These combinations of sinusoids that are all the fundamentals of octave-related notes are called shepherd tones. And if you shape them like this, so they die away gently at each end, you can do these really interesting illusions where you can have a tone whose frequency always increases, but whose average spectrum stays the same. So it's an endlessly rising tone. That's where it was Roger Shepard and Jean-Claude Risset who came up with those originally. So we can use these to resynthesize, and then if we resynthesize the piano, the semitone, the chromatic scale on the piano, we get this. So it sounds a bit weird because it sounds like there are multiple notes playing, but you get the idea that the scale is going up, but in fact, it never stops. You can keep going indefinitely for that. So let's try that on Let It Be. So here's the original. Here is the chroma features, and now these are the notes on one octave of the piano, and you can really see what's going on here, right? So it starts off with a C major, C, E, G, and lo and behold, we see this pretty clear C major, and then this is what G major, or is it G? G major, yes, G major. So again, G, B, D, whatever. So there are reasons why it isn't exact, right? Which is because it's not just C in here, but there are harmonics of the C, and the third harmonic of C is also a harmonic is the fundamental of G at something. And so at some point the harmonics start being unrelated to the actual notes that are present. But it works surprisingly well. So we get the chroma features, then we can resynthesize using the shepherd tones. So now each one of these has been realized as a whole bunch of sinusoids. But these sinusoids carry the pitch, albeit with the octave removed. And in fact, I think these are quantized, so they're quantized pitches, but even so, there's quite a lot of dynamics in here. But there's no spectral shape at all. So now we can use this as the thing we filter with our MFCCs, right? Rather than just using white noise, we can say, oh, we've got some idea of what the fine structure is. And so then we can get this, which is the MFCC filtered shepherd tone. So here's the shepherd tone only resynthesis of Let It Be, the third line. So it sounds like this kind of organ tone. But the notes, and to some extent the harmonies, are still preserved. The voice it has much more trouble with because it's quantizing the pitch, so it can't deal with the slides. And it's mixed in with the piano notes, right? It's no longer distinguishing between the notes that are due to the voice and the ones that are due to the piano, and so it's much more ambiguous. When we then apply the MFCC shaping on top of that, it sounds the same to me. It's not what it's meant to sound like. Oh no, yes, okay. I don't know what happened there. Hang on, let me play it for you properly. So it still sounds kind of organy, but it's not super bright like the other one was. So it's kind of interesting there that the MFCC allows us to recognize the voice, and there it's sort of, because there are some pitches in there which are related to the voice and some which are not. it's, it's not a terrible replica, although it's not something you'd listen to for pleasure.
Should maintain the chord from piano and also recognize the pitch of the vocal.
Right, but it's not separating the notes from the piano and the pitch at all. They're mixed in. There's only one set of pitches for any time, but the MSCC is saying, well, it's got some energy down here, which should be for the piano, and some energy up here, which is for the voice. And then it's up to us to sort of say, well, I'm going to hear this pitch with the voice, and this is the accompaniment, which you can sort of do sometimes. I don't want to claim too much there. Stop. Okay. So that's kind of interesting, because now for every 10 millisecond frame, we've got 12 chroma bins and 20 MFCC bins, and we're able to reconstruct something. But if we want to do some more kind of high-level modeling, then it's still quite a lot of dimensions, because we've still got 20,000 frames like that. And so there's this work which is which I've done a bunch of, although I wasn't the originator of it. I'm crediting Barch and Wakefield as doing the stuff, which is where, rather than representing every 10 millisecond frames, you actually do beat tracking, and then you represent every individual beat segment. And so last week we saw about the beat tracking, so the beat tracker on this. Actually, it turns out this is kind of a hard thing to beat track because of the syncopation between the voice and the piano, but I think this is the beat tracker. Yeah. Right, so that's just the beats that it's finding. And then I can stop this. You see, it just sort of follows his rhythm rather than the piano in there. But anyway, we say, okay, now we've got this sort of time base which is related to the music. So now I'm just going to take my features and I'm going to average the chroma within each of those beat length things. And so I'm going to, now the beats can't change, the notes can't change within a whole beat. And then we can resynthesize from that, which is, I think this is just Shepard tones, there's no MFCC shaping. So you can feel it pulsing as the chroma get updated. So it has a lot of trouble when the voice comes in because the beat tracking is not doing so well, and of course the voice wants to change pitch within a single beat, but it can't. It's constrained not to. But it's remarkable how, even like the nice cadence, that makes sense. Like, yes, well, the notes did only change on the beat, and so you get the final cadence correctly. So this is now a pretty compact representation. Right? This is 12 values every few hundred milliseconds, so you can get the whole track in maybe 1,000 time frames. And so this is something we've used a lot for different kinds of as a relatively low-dimensional but high information content description of the music. So one of the things you can do with this is to try and do chord recognition. Now it's like, you could do it on the raw 10 millisecond frames as well, but in some sense, if you can average them over a longer time frame, as long as they are consistent within that time frame, then averaging will sort of clean them up, make them, reduce the amount of random variation. And so it's a nice basis for chord recognition. And so here, the beat synchronous chroma for the beginning of Let It Be, and you can really see the piano chords very clearly there. And so you can say, okay, well, I'm just going to say that I'm going to call this C major, and I'm going to take a bunch of examples of this, and I'm going to try and learn the nature of C major. So we're running out of time here, but this is what we're going to play with on Wednesday, which is the system we built for recognizing chords using beat synchronous chroma and using Gaussian models in chroma space to represent each chord. And lo and behold, it actually uses a hidden Markov model to smooth out the sequences of chords. And of course, there are interesting sequential constraints in the chords that if I tell you I'm in C major, then there's different expectations than what the next chord is going to be. Technically, to do that, you need to know what key I'm in, right? If it's C major and C major, then you expect me to go to F or G or A minor or something. If it's C major in some other context, the expectations will be different, but it's not uniform across all different chords. And so that's what this system does. It takes chroma features here. It actually took chroma in two different frequency ranges, because one is sort of getting the bass notes and one's getting the melody or main voicing notes. And then it has these Gaussians. It has one Gaussian for each root from C to B, C, C sharp through to B, so each of 12 roots. Then it has different models for the major chords and the minor chords. So it has 24, but it only knows 24 different chord labels. It has models for each of those. And then it has a transition matrix which says, well, given that you're in one of these chords, what is the likelihood you're going to go to a different one? And that looks kind of like the answer is mostly if you're in a certain chord, you're going to stay in that chord, which of course is the most likely thing. But it does capture some of the off-diagonal structure as well. And then there are some other things we did, but I guess I'll talk about them on Wednesday when we have a go with this. So any questions before we break up now? All right, I'm sorry we didn't get through all this, but we'll figure it out on Wednesday.